Hello students, welcome to lectures on complex numbers. In the previous lecture, we introduced polar representation of complex numbers. Let me recall polar representation of complex number. Given any complex number z can be given by the representation r multiply cos theta plus I sin theta, where r denotes the distance from the origin to this complex number and theta denotes the argument which is lies between 0 and 2 pi. And let me again recall the same number can have different angle because of cos and sin as periodic function with period 2 pi. So, which means the same representation holds for different theta value where the argument again this theta plus 2 k pi, where k for some integer. Let us try to see again a simple example. So, when we consider a point, let us say the complex number 1 plus I, we have in the last class we seen that the angle is the theta is pi by 4 or 45 degree, and what we observe is you can add say 2 k pi. It means that from this particular axis we can also view this point as like added with the 360 degree to this line. Once you rotate by a 360 degree you reach the same place, and that is reflected through this say by these periodic functions. We see that the same theta can have with the addition with the 2 k pi. Okay. So, let us see that one more point which is I consider it as its conjugation, that is 1 minus I. The angle made from the x axis we see that it is 2 pi minus pi by 4. The angle here it is 2 pi minus pi by 4, and which is same as 7 pi by 4. The same angle can be realized by taking the clockwise direction from the x axis, which we denote minus pi by 4. The reason is, you see here when we are measuring the angle to the x axis, we are making the angle in the anti-clockwise direction, that is counter clockwise direction. So, that we are taking as a positive way measuring the angle. Now, we are going in the opposite direction. So, in this way we are basically denoting the minus pi by 4, and here if we write with respect to this theta value, what we see is 1 minus I, and the representation r denotes the modulus of complex number, which is root 2 cos of 7 pi by 4 plus I sin 7 pi by 4. We can also verify that this is same as with respect to theta as which is minus pi by 4, that is cos of minus pi by 4 plus I times sine of minus pi by 4. This is easily verifiable because you see that cos function is a even function and use that sine function is odd function. Using this, immediately we see that this particular quantity is equal to 1 minus I. So, the value of we have cos of pi by 4 is 1 by root 2, and similarly the sine of now again just repeat the z as the polar representation r cos theta I sin theta. To make a unique representation, we restrict ourselves to theta value 0 to 2 pi, and what we observed is it can be with the theta plus 2 k pi with k varying in the integers. Now, what are the say results we discussed in the last class? One is the nice formula, that is De Moivre's formula. We showed that cos of using this formula cos theta plus I sin theta, our n is cos n theta plus I sin n theta, and we saw at the end using this relation we derived some trigonometric identities, and now we continue our discussion about the division, how we do using this polar representation. Suppose we have two complex numbers z1 in the polar representation r1 cos theta 1 plus I sin theta 1, z2 is r2 cos theta 2 plus I sin theta 2. The division we can let us derive directly. When we divide r1 cos theta 1 I sin theta 1, r2 cos theta 2 plus I sin theta 2, here we can to get the inverse multiply by the conjugate in the denominator. So, we get the numerator multiplied with the factor which is conjugation of cos theta 2 minus I sin theta 2 divided by z into z bar is nothing but mod z square. So, which means what we get is the denominator cos theta 2 square plus sin theta 2 square, which gives 1, and observe the numerator. Numerator just focus on the real part, cos theta 1 multiplied with cos theta 2, and other term comes with the plus sin theta 1 sin theta 2, that is nothing but cos of theta 1 minus theta 2. So, the real part we get cos of theta 1 minus theta 2 plus I sin theta 1 minus theta 2. So, let us recall the multiplication of two complex number. What we observed is we multiply the magnitudes, that is r1 r2, and then the angles are summed up. Now, what we observe is angle is subtracted when we are doing the division. Let us do a simple example. Consider z1 as 1 plus I and Z2 as I. Let us view in geometrically what these numbers are represented in the Argand plane. We have the point 1 plus I somewhere here, which makes the angle 45 degree, and I, which is making an angle 90. Now, by division, what we observed is we need to divide the its modulus. Modulus of Z1 is root 2 and modulus of Z2 is 1. Now, so first of all, let us write in the polar form. Z1 is root 2 cos pi by 4 plus I sin pi by 4, and Z2 is modulus is 1 and cos pi by 2 plus I sin pi by 2. Now, the division we need to subtract the angle. So, this gives us cos minus pi by 4 plus I sin minus pi by 4. So, what we are getting is a vector with a minus 45 degree. As I mentioned, the minus sign denotes that it is measured from the x axis in the clockwise direction. So, a vector it goes of this with the 45 degree in the opposite direction. So, again the as we noticed previous slide, it is 1 by root 2 and here it is minus 1 by root 2. So, what you get is, which is just the minus 1 minus I, right. So, let me just make a simple remarks here, that what we observe is when we divide, we observe that it modulus given by R1 by R2, and we know what is R1, it is modulus of Z1 and modulus of Z2. And one important point I missed to mention, we make the division basically with the Z2 is non-zero. Okay. This is always say to, then only it is to make sense. Okay. And one more remark, which extends the De Moivre's formula. So, when we are considering z power n, we are going to see cos of theta plus I sin theta, with n being minus 1, minus 2, thus n equal to minus 1. It means that, excuse me, so that is z power minus 1, that is 1 by z, which means that you divide by cos theta plus I sin theta. 1 is also treated as the complex number where angle is just 0, which means what you are going to get factor is, for this it is, we need to say the modulus for each factor is 1. So, it is just 1 by 1 and we need to subtract the angle from the angle for the number 1, okay, that is just the 0 minus theta plus I sin 0 minus theta. So, it means it is cos of minus theta plus I sin minus theta. For n equal to minus 1, we get this, and By doing in a similar manner, we can verify that z power minus 2, this is nothing but 1 by z square, which is 1 by z into 1 by z. We just notice that each factor comes as cos of minus theta plus I sin minus theta. Again it is basically the same factor square. We know basically by the de Moivre's formula which we derived for positive integer, we get it as cos of minus 2 theta plus I sin minus 2 theta. So, by induction we can show that when n is negative integer, we can show that it is cos of n theta plus I sin n theta. So, as a result, combining the positive integers we already verified, now we verified for negative integers. So, by combining these two, we see that for n belongs to integer, this relation holds, that is cos theta plus I sin theta power n gives cos of n theta plus I sin n theta. Now, let us do a simple example. We would like to say calculate the value for 1 plus I root 3 power n plus 1 minus I root 3 power n, and what we know is the polar representation for this. We need to calculate first modulus. Modulus is 2 and we need to calculate theta. Theta we can verify that it is pi by 3. So, here it is for say tan inverse for, thus we have pi by 3. So, it is cos of pi by 3 plus I sin pi by 3 whole power n. Similarly, we need to do for 1 minus I root 3. So, again the modulus is same, which is 2, and the angle is, if you observe, it is just in the anti-clockwise direction. So, it is because it is just the mirror image, that is a conjugation. So, it is 1 plus I root 3 and this is 1 minus I root 3. So, if this is pi by 3, then this angle is minus pi by 3. So, this is minus pi by 3 plus I sin minus pi by 3 power n by the de Moivre's formula. What we observe is the quantity here, it is 2 power n. So, the argument n, the power n goes with the multiplication in the argument. So, we get cos n pi by 3 plus I sin n pi by 3, this is first term, and the second term 2 to the power n, and use that fact. So, apply the again this formula, we see that it is cos of minus n pi by 3 plus I sin minus n pi by 3, and after using the fact that cos is a even function and sin is a odd function, we see that these two factors gets cancelled and we get twice of this term, which is 2 to the power n plus 1 cos of n pi by 3. So, what we observe is when we are calculating power of complex number, it seems that using the polar representation we can easily calculate. Now we are going to discuss something which is very fascinating fact, that is the nth root of unity, roots of unity. So what is the question here? We look for complex number whose power is raised by n gives 1. Okay. So we are going to ask what are all the complex numbers whose power n gives value 1. Okay. So such a complex numbers is called nth root of unity. Now let us observe, so once we demand a complex number satisfies this equation, then immediately you observe that modulus of z must be 1. Okay. This is first observation we make. Suppose there is a z0 in complex numbers such that z0 power n gives 1, then immediately we observed modulus of z0 must be 1. So from this equation we see that modulus of z0 power n and modulus of 1, this must be satisfied, and we know that mod zn is same as mod z power n and modulus of 1 is just 1, and now this is just what we are asking is a real number, non-negative real number whose power is say raised by n, when this will be equal to 1. This happens only when mod z0 is 1. Okay. So in the real numbers. Now with this observation let us try to discuss with the simple cases, like taking n equal to very specific values, we will try to observe what are the numbers satisfies this equation with fixed value of n. Let us fix, say, let us start with just say n equal to 1. Okay. If n equal to 1, the power basically what we raise just 1, this must say, this implies immediately just it is a single complex number just 1. Okay. So now first of all let me just repeat the observation what we made. When we are looking for nth root of unity, any complex number satisfies this equation, then corresponding modulus of say the complex number must be 1, which means it must lie on the unit circle. Okay. So now I have taken n equal to 1, then it just means that only one point which is z equal to 1. Now if I take n equal to 2, then we are demanding say z square equal to 1, and simple say observation we can see that this implies z equal to plus or minus 1. So let us say that first number is 1 and second number is minus 1. So what we observe is when we take n equal to 2 and we are asking what are all the complex numbers whose square is 1, we observe that when we consider z equal to 1, z equal to minus 1, it satisfies this equation. Okay. So somehow what we are say observing is it is like given a 360 degree, it somehow just divides by 2. Okay. So, here it is like 360 degree, it just divide by 1, then only one factor we got. Now, we have power is 2, then we divided 360 degree in 2 factors, and which is basically like one factor which is appears at the like angle which is pi, and another one which is appeared in 0. If you again rotate by pi, we get 360, which is again 1. Okay. So, now with this observation we are going to just write without thinking for the case n equal to 3. So, we consider n equal to 3, and our question is what are all the complex numbers whose cube power is 1. Okay. So, without say thinking, I am just going to apply the previous observation, that is we are going to divide this 360 degree angle by 3 parts. So, when I divide, which is basically gives something which is 120 as a degree, then if I sum up, then you get a another term here. Now, I am not sure whether its power is say gives 1, okay. But now you just see that it is, you just try to write the polar representation for this number. What is it? It is, let us call say Z1 as 1, Z2 as the term with the angle which is cos of, since it we have collected a point from modulus 1. So, modulus of this number is 1 and angle is 120 degree plus I times sine 120 degree. Now, if you raise the power 3, we get here by the de Moivre's formula, the power will be multiplied to the argument. So, which means the cos of 120 degree plus I sine 120 degree power 3, which is going to be multiplied for the each argument, which gives us 360, which is cos of 360 degree plus I sine 360 by de Moivre's formula. So, we know what is the value for this, it is 1 and this factor is 0. So, what we observed is Z2 cube gives 1. Similarly, one can verify Z3 if you remember how we are how we are getting, it is basically angle were equally divided, which means you add one more 120 to this particular from this particular line, and if you recall the angle sum is happening when you are multiplying it. Okay. So, when say this is basically originally 120 degree comes from Z2 and Z3 is nothing but you multiply from by Z2 itself. Now, you take the power 3, you see that say each say Z2 cube is 1. So, we see that it is 1. So, now let us do the same say observation, continue for n equal to 4, Z to the power 4 equal to 1. We are asking now what are all the complex numbers whose fourth power is 1. Okay. So, again the idea is we are going to apply the same observation, that is we are going to divide the angle by 4, which we get it as pi by 2. So, which is as a default what we observe is when you take Z1 say as 1, it always satisfies this equation. So, which means 1 is always basically a complex number which satisfies this, and further we add the pi by 2 which is I, and this is minus 1 and minus I, and we can easily verify that whose power say 4 gives 1. So, here we see that Z1 is 1, Z2 is I, Z3 is minus 1, Z4 is minus I. Okay. Now, whatever we observed till now, let us write it as a general frame. So, we are considering say our interest to find the nth roots of unity. So, which we are say, which means that we are interested in a complex number whose nth power gives 1. Now, try to use whatever we have observed now. The 1 can be written as cos of 2k pi plus I sin 2k pi. Okay. So, before going to this, let me add some more comment to the previous slide. What we observed here is we found like 4 numbers which satisfies this equation. The question in our mind is whether these are the only 4 numbers satisfies this or more. Okay. This is not answered. Okay. So, you need to remember this. Now, Z, the complex number which we are looking for, let us write it as say cos theta and I sin theta power n. By De Moivre's law, what we know is this is cos n theta plus I sin n theta, which gives cos 2k pi plus I sin 2k pi, where k is from integer. Okay. For simplicity, we are going to just say go from 0, 1, 2 and so on. So, what we observe is from this we would like to ask what are all the theta values for which this equation satisfies for some k belongs to the integers. So, very naturally what we see is that if theta for theta, if we choose as 2k pi by n with k from 0, 1, 2 and so on, then what we see is that this equation satisfies for these values. So, let us call it as equation 1. For theta, equation 1 holds. Okay. Now, so this particular equation tells us these are the only possible values which can satisfy this equation. Okay. So, that is the first observation we make. So, we are basically like when we are considering a complex number power n must be equal to 1, and we try to ask what is the argument for this complex number, we end up that the theta must be of this form. Now, question is what are all the distinct theta values, so that it gives the distinct complex numbers. Okay. So, here I would like to mention that I use the fact here, the observation here, that is mod z must be 1. Okay. So, in this equation we used mod z equal to 1, that is why we basically like did not write this fact. Now, our interest to find the distinct theta values from this particular argument. Okay. So, what I observe is I define theta k as say 2k pi n with k from 0, 1 etc. till n minus 1. Okay. So, I only collect the values for k from 0 to n minus 1. For each theta k I can define a complex number. So, let and define zk the corresponding complex numbers, which is cos theta k plus I sin theta k. Now again k is from 0, 1, etc. this. What I know is from the derivation it follows that these numbers are nth root of unity, power n is 1, okay, for all k from 0, 1 to this n minus 1. Now question is whether these are the only complex number, which means can I take k value other than n minus 1, may be negative or more than n minus 1. If I take, we are going to show that it will be equal to one of the zk, okay, that is what we are going to prove now. So what we will show is, our claim here is you collect these sets, that is say zk in a similar manner you define it from integers. For each integer you can associate a zk, and we are going to show that it is only a finite set, which is just the zk's with k from 0, 1 till n minus 1. Okay. So to prove this, what we need to show is just this set is just contained it here, because it is obvious that this particular finite set of number, it is subset here, and immediately we see that the set is contained it here. We need to show that any element here, it is of this form. Okay. So to prove this, let us consider an integer, let us call it as, let us say r, which is in the integers, and we consider zr, which means corresponding theta r is given by 2r pi by n, okay, and correspondingly we have the zr, okay, right. Now we need to observe this factor r, okay. So r can be say by quotient remainder theorem, that is any say integer can be factored, because n is a positive integer given to us with a remainder, let us say k, where q is a number from integer and k is element in 0 to n minus 1. So now just apply this, theta r is 2 pi q n k by n. So the first factor what we observe is it is 2 pi q plus 2 k pi by n, and we know that if a argument differ by 2 pi integer multiple, we are going to get the same complex number. So which means the number which is the zr here given by cos of 2 pi q plus 2 k pi by n plus I sin 2 pi q plus 2 k pi by n, and using the periodicity of cos and sin function, we see that it is cos 2 k pi by n plus I sin 2 k pi by n. This is nothing but our element zk, which is associated to the we can write this as theta k. So, what we showed is any, say for any given integer, you consider the corresponding argument, you define the corresponding complex number, this must be equal to one of the zk. So, which means that now what we derived is the nth root of unity is, now we can define nth roots of unity for, that is z power n, are these zk's with, which is defined by cos of 2k pi by n plus I sin 2k pi by n with k values from 0, 1 till n minus 1. Now again just repeat whatever we have done before. For example, like we take n equal to 1, I think that is trivial case. Let us take the n equal to 2, then we are looking for z square equal to 1, then here z1 is given by, so we by this index notation z0 which is given by, so here n is 2 and for the first k value is 0, so cos 0 is 1 and sin 0 is 0, z1. So what you see is that this is cos of pi plus I sin pi, we get minus 1. Similarly n equal to 3, we see that for the equation z cube equal to 1, we get z0 as 1, that is common one. Z1 is cos of k equal to 1, n equal to 3, so 2 pi by 3, which is nothing but the 120 degree, plus I sin 2 pi by 3, and z2 is, which is cos of k value is 2, that is 4 pi by 3 plus I sin 4 pi by 3. Now let us try to visualize this in the geometrically. So when we take the nth root of unity, drawing circle is really difficult for me. Okay, just assume, imagine that we have this bigger circle. Now what we observed is, when we calculate the nth root of unity, take k equal to 1, then it is 2 pi by n. So we have the whole, say, angle which is 2 pi. Now you segment this by n terms. Okay. So we are equally segmenting it. So if n is, let us say that if n is 8, then we are going to segment the angle by 8. So we get, say, pi by 4, we get pi by 4, pi by 2, and then further you make a division here, and we are getting this one. So if you closely look this, then what we are getting is, for each segment you are dividing in a equal arc length. Okay. For each division angle, because each time what you are having is the angle is 2 pi by n. So when I write theta 1, which is 2 pi by n, and next angle which is going to add. So, theta 2 is, say you are going to add this term, that is 2 pi by n plus 2 pi by n, which means the equal angle we are going to add it. Okay. So, which means if I try to place a object like a polygon on these vertices, okay, then what are you going to get is a n regular polygon. Okay. So, for example, for n equal to 8, if I like to place a polygon, then what I get is, it is okay, it is difficult to visualize from this circle which is drawn badly. Okay, okay. So, we see that there are 8 faces for this polygon, and what we see is that each sides are equal and each angles are equal. By the definition, what we are getting is a regular polygon if we place on the nth root of unity. So, let us write down this geometrical observation. The geometric image of the nth roots of unity are the vertices of a regular polygon with n sides inscribed in the unit circle. With one of the vertices at 1. This is, let us call it as remark 1. Remark 2, if you look back the definition Z1, if we look back the definition of Zk is k equal to 0 is a trivial one, that is 1, and let us consider Z1. Z1 is cos 2 pi by n plus I sin 2 pi by n. Now, if you take the power Z1 square, we get by De Moivre's formula that the power multiplies with the argument. So, we get cos 4 pi by n plus I sin 4 pi by n, or in general if I take kth power, then we get 2 k pi by n plus I sin 2 k pi just by the De Moivre's formula. We get this. Just recall what is this? This is nothing but your Zk. So, what we observe is these Zk's, that is the remaining nth root of unity, it is just the generated by Z1. Okay. So, if I write down the set, the nth root of unities, the nth root of unities, we have set which is Z0, Z1, Z2 and so on till Zn minus 1. This is just given by Z1 power 0, that is 1 power 0 1, and Z1 power 1 we get Z1 itself, Z1 power 2 we get Z2, and z1 power n minus 1, we get zn minus 1. So, which means the nth root of unity, it is just generated by this element z1. If you have only the z1, we can just calculate the remaining elements just taking its power. Today's class we introduced nth root of unity and we just discussed that it contains n distinct elements for the nth root of unity, and the set is generated by the single element. For example, the z1 generates the remaining all elements. So we continue the other properties of the nth root of unity in the next class. Thank you.